Okay, section 18.6. Now what we're going to do is we're going to connect free energy to our discussion of chemical equilibrium. In this course, we've covered a lot about chemical equilibrium. And now we've started introducing the idea of free energy. Let's connect the two. So the way I'm going to do that is I'm going to point out that if we're under standard conditions, all right, if we're under standard conditions, we use the symbol for free energy change, delta G with a little degree sign there, right? What that generally means is that if we are dealing with any gases, their pressures are 1 atmosphere. So in other words, if we have a gas in a chemical reaction, the pressure is some pressure greater than an atmosphere or less than an atmosphere, and then that's non-standard conditions. For solutes in water, we call those aqueous, right? The concentration of the solute in molar units should be 1 molar. Okay, so if the concentration of a solute is less than 1 molar or greater than 1 molar, then that's a non-standard condition. So when we look these values up, whether it be the standard enthalpy of formation or the standard absolute entropy value or the standard free energy of formation data, those are the assumption, two of the assumptions is that if it's a gas, the pressure is an atmosphere, all the substances involved in producing that substance, all the gases are 1 atmosphere, and for anything dissolved in water, the concentrations of any solutes would be 1 molar as well for that process, okay? But it is often the case that we're not under standard conditions. So how do we calculate delta G if we're not at standard conditions, right? So for example, what if the temperature is different? What if the pressure is not 1 atmosphere? How do we deal with that? Well, there's an adjustment that we can make. So we don't have to have a table for every possible condition. We're going to say that the free energy change under non-standard conditions is equal to the free energy change under standard conditions plus an adjustment factor. And the adjustment factor is RT ln Q, where R is the universal gas constant, right? We know that value. R is 8.314 joules per kmol. Temperature, right? Should be in Kelvin. And Q is the reaction quotient. This is what we discussed way back in chapter 15 and 16 and 17, okay, the reaction quotient. So it turns out that the adjustment to the free energy change for non-standard conditions is related to chemical equilibrium, okay? So for example, suppose we have this reaction here, H2 gas plus I2 solid goes to 2HI gas. Let's read out the reaction quotient. Okay, actually I'll give you a couple of numbers here. Let's say that the pressure of H2 is 4 atmospheres. And the pressure of HI is 3 atmospheres. Okay? Now, suppose I wanted to find out what Q is. We'll call it Q sub P. It would be the pressure of HI squared divided by the pressure of H2, right? We wouldn't include the I2 because that's a solid, right? Heterogeneous equilibrium. We don't include solids or liquids in our expressions. So Q sub P would be 3 atmospheres, or 3.0, squared, divided by the pressure of hydrogen, which is 4.0. So that's 9 over 4, which comes out to 2.25. Okay. Now, suppose that I was able to calculate this. We can do this from free energy of formation data, and I say that it's positive 2.60 kilojoules per mole. And of course, this is taken at 298 Kelvin, so let's assume the temperature is at 298 Kelvin. Let's find delta G under these conditions. Delta G would be delta G naught, which is 2.60 kilojoules per mole, plus RT ln Q, so plus 8.314 joules per kmol. So that's R, 298 Kelvin, times the natural log of Q, which would be the natural log of 2.25. Okay? So one issue that arises here is that the delta G naught is in kilojoules per mole, but R is in joules per kmol. So we can resolve that issue by converting the delta G naught into joules per mole. So kilos 1,000. So this is really 2.60 times 10 to the 3 joules per mole. Okay? So we could add that to the next term, 8.314 joules per kmol, 298 Kelvin, natural log of 2.25, which is unitless. And what you get is 4,300 joules per mole, or 4.3 kilojoules per mole. Okay? So we can calculate delta G under non-standard conditions just by using that situation. Now suppose I change my initial conditions. Suppose I say I'm no longer going to use 3 atmospheres for HI and 4 atmospheres for H2. Suppose now I say the initial pressure of H2 is, I'm going to keep that at 4. But now I'm going to change the pressure of HI to 1. What happens to Q? Again, Q is the pressure of HI squared over the pressure of H2, right? We saw that before. So in this case now we would have 1.0 squared divided by 4.0 to the first power, right? So now, what do we get? 1 squared over 4 is 0.25. So Q is 0.25. Now here's what happens. If we want to calculate delta G for this one, again, we would have 2.60 times 10 to the 3 joules per mole plus 8.314 joules per kmol, 298 Kelvin, ln of 0.25. And what's interesting about this is when you take the natural log of 0.25, you get a negative number. It's less than 1. So this term here becomes negative. This term here is positive. So what happens is interesting. If this term here is more negative, this one here, is more negative than this one, then overall this will be negative. If overall delta G is negative, that means it's spontaneous. And that's exactly what happens. What this becomes is overall negative 800 joules per mole, which is in kilojoules per mole, negative 0.8. So these initial conditions result in a spontaneous process, even though originally our calculation, right here, was non-spontaneous. right? Positive is non-spontaneous for delta G. And even under standard conditions, it was non-spontaneous. What that tells us is we can make a reaction become spontaneous by affecting or varying the initial pressures or concentrations if we're dealing with aqueous solutes. So essentially what happened here is this. Q is less than K. And if Q is small enough, the reaction, according to Le Chatelier's principle, will move towards equilibrium, right? Right? So if Q is less than K, the reaction goes to the right so that Q can approach K. So what does that mean? You're going to form more products. In order to form more products, that means you're going to the right. That means the reaction to the right is a spontaneous process. For the reaction to be spontaneous, delta G's got to be negative. Okay? Isn't that interesting? So what that tells us is that if Q is greater than K, delta G will be positive, and if Q is less than K, delta G has the potential to be negative and for that process to be spontaneous. It's very interesting. So try the sample problem on that. 18.8 is a very interesting example of that, of how you can look at that. Okay? Now let's move on to the next issue, which is connecting delta G to the chemical equilibrium constant, K. So we saw the relationship between delta G and Q, but now we want to look at the relationship between the equilibrium constant. So remember, K is our equilibrium constant. Right? Q is the reaction quotient. They're related, right? But they're not the same. The reaction quotient is the products over the reactants under any conditions, standard or non-standard. The equilibrium constant is the products over the reactants if we're at equilibrium. Okay? And then we have delta G, which is standard or, non-standard conditions. And then we have delta G naught, which is under standard conditions, more stringent. Right? 1 molar for solutes, 1 atmosphere for gases. Okay? So what I'm going to do is I'm going to say the following. I'm going to come back to this equation here, delta G equals delta G naught. By the way, I never showed you how this equation arises, and we're not going to do that in this course. That's something we do in a different and more advanced course. So let's imagine that we are approaching equilibrium. If we're approaching equilibrium, what that means is delta G is approaching 0. Right? It's getting closer to 0. That's what we said in the previous section, which is if the change in free energy, if we're at equilibrium, the change in free energy is equal to 0. Okay? So as we approach equilibrium, delta G is going to approach 0. But something else happens. Q approaches K. Q becomes K. So let's make those two substitutions right there in our equation. Delta G is going to approach 0. So 0 is going to equal delta G naught plus RT ln K. So if we are at equilibrium, Q becomes K, right? That's what equilibrium can be thought of, is when Q, the reaction quotient, is equal to K, the equilibrium constant. We now can subtract the second term, RT ln K, from both sides. So now we would have that delta G naught is equal to minus, remember we have to subtract it from both sides. This now gives us an interesting relationship. It relates the standard free energy change for a chemical reaction to the value of the equilibrium constant. It gives us a powerful method for converting between the two. Equilibrium we thought of as pressures, concentrations, energy, joules, kilojoules, free energy, enthalpy change, entropy changes. energy and equilibrium are actually related through this equation. If we know the value of K, if we measure in a laboratory, we can now find delta G for that process, the energy associated with it. Or vice versa. If we know the energy change, we can find K. Let me show you how you would do that step. If we wanted to find K, what I'm going to do is I'm just going to take delta G naught. I'm going to divide it by RT. And then I'm going to multiply the equation by minus 1. So that'll make that a negative. And that would be equal to ln K. So we've almost got K, but not quite. So how do we get K? Remember, ln of e to the x is equal to x, or e to the ln of x is equal to x. Those are inverse functions. So if I do e to both sides, e to the minus delta G naught over RT, that would be equal to K. So here's our second relationship. So in other words, if you can somehow use your Appendix 2 data, this you sometimes can get from data, free energy change of formation, If you have that data and you know the temperature, you can calculate the left side of the equation and figure out what K is. Or, if you know what K is, you can use this equation and find out what delta G is. It's really very interesting. So let me show you just one quick little equation here. One quick little example of this. Suppose that we have a reaction like N2 plus O2, and that's in equilibrium with 2NO. And we happen to know that Kp is 4.0 times 10 to the minus 31. Okay, so we've measured that. And this is at 298 Kelvin, right? 25 degrees C. Could we find delta G for this reaction? Delta G naught? Well, according to this equation right here, we can, right? Delta G naught is minus RT ln K. That's all we need. So let's come through it. Delta G naught would be minus. Now, I'm going to use a value of R that's in kilojoules per Kelvin mole. It's 0.008314 kilojoules per K mole. Okay, so not joules per K mole, but kilojoules. So you have to just add to move the decimal point over 3 places. 8.314 becomes 0.008314. The temperature is given, 298 Kelvin. And now that would be times the natural log of 4.0 times 10 to the minus 31. Okay? And that would give us delta G. Now let me ask you a question. Do you think this answer, this delta G, is going to be positive or negative? Let's think about it. There's a negative in front, right? There's a negative right there. But the question is, when you take the log of a number, is it going to be positive or negative? And here's the way to tell. The log any base of 1 is equal to 0. So if the number you're taking the log of is less than 1, even 0.999, that's less than 1, right? It's going to be negative. If the log is greater than 1, it's going to be greater than 0. It's going to be positive. Okay? So that number, 4.0 times 10 to the minus 31, that is certainly less than 1. I'm not claiming it's a negative number, right? I'm not saying you're taking the log of a negative number. We can't take logs. They're undefined for negative values of x. But if the number is less than 1, even 0.999, the log of that will be negative. So let's go ahead and run it through. 4.0 times 10 to the minus 31. There's our big small number, right? Our very small number. Let's take the natural log. There you go. See how it's negative? Now, let's multiply it by RT. 0.008314, 298. But remember, we said it was negative, so we're going to multiply it by -1, and it becomes 173.4. I'll just round it to 173. Remember, this was kilojoules, right? So the moles cancel. Oops, sorry, the moles do not cancel. Sometimes I get excited about canceling units. I go a little bit overboard. The Kelvin cancel. So you got kilojoules per mole. So what that tells us is that under standard conditions, this reaction is non-spontaneous, right? By quite a bit, 173 kilojoules per mole. In order for it to be spontaneous, delta G would have to be negative under these conditions. So we can tell from the equilibrium constant whether something is spontaneous or not. A reaction is spontaneous. So for example, if I said, hey, I'm going to take this reaction right here. This is actually not really reversible. It only goes in one direction. But K, let's say K is equal to 10 to the 82, for example. Very huge, bigger. That right there, this is going to be a spontaneous reaction, right? Because delta G, not, is going to be minus RT ln 10 to the 82. That's definitely going to be positive. It's greater than 1. You have a negative there. A negative times a positive is negative, so this is going to be negative, and you know that's going to be spontaneous. Okay? So a reaction is spontaneous essentially because there's free energy waiting to be released. So when something has energy, and that energy can be released in some way, right? The energy is going out to the surroundings. We're going to use G for energy. If this is the reactants, and this is the products, this will be a spontaneous process. Energy can be released. In other words, delta G is negative, right? That's what that means. G is decreasing. It's releasing energy to the surroundings. If delta G is negative, that means it's a spontaneous reaction, which means you're going to get products, right? You're forming products relative to reactants. So free energy, equilibrium, very powerful relationship.